Hello Internet, my name is Quinn and this is Blondihacks. Today I'm going to finish the wheel sets for the locomotive on my Pennsylvania A3 switcher. We're going to make the pump drivers, the eccentrics, and we're going to quarter the wheels. I know the steam nerds are waiting for that one. We've got a cool fixture that I'm going to show you for doing that, and I'm going to explain what quartering is, all that and more right now. Here's where we left things. We've got a fake rolling chassis, fake because the wheels aren't actually attached. Now on the solid rear axle, we need to attach some eccentrics. And an eccentric in steam and early internal combustion engines is kind of a forbidden love child between a cam and a crankshaft. And it's a way to drive a mechanism off of a shaft while allowing the shaft to go all the way through. I'm going to use this piece of free machining steel to make two eccentrics. We need one to drive the main water pump for the locomotive and one to drive the main oil pump. Or in proper choo-choo jargon, that would be a mechanical lubricator, which is driven from the axle. I'm ensuring with the parting blade and a scale that I've got just the right amount of stick out in front of the chuck, because I want to be working as close to the chuck as I can. I'm going to be doing a couple of fairly high tool pressure operations. Making eccentrics is always pretty interesting. There's a lot of neat operations in this one, but we'll start with the traditional, facing of the end, of course. Next, I'll turn the OD to match what's in the drawing. Nothing too fancy here. Eccentrics are certainly not the only way to drive accessories like this on a steam locomotive. Locomotives did this all kinds of different ways. Pretty much anything that moves on a locomotive has probably been used by some designer to drive a mechanical lubricator or a water pump. For example, this is CPR 2816, the Empress. This is a 464 Hudson class locomotive, and it taps power off of the valve rod to drive the mechanical lubricator. So anything that moves can drive something. Next up is a groove down the middle of the eccentric, and this is where the eccentric strap rides. It's a kind of a clamp looking thing, not actually a clamp, but it's like it looks like a connecting rod in a piston engine if you've seen one of those. It wraps around the eccentric and rides in this groove, and this is what actually converts the rotary motion to linear motion. Accuracy is important for this groove on both depth and width to make sure that the eccentric strap rides smoothly in there with no play and no rattle, but of course still moves smoothly. I'm going to do this the way you see me do a lot of this kind of feature. I plunge into a depth 5 thousandths short of the final depth in a couple of passes with the grooving tool. Then on the final cut, I'll pan across the bottom of the groove, taking a light skim cut to even everything out. I find this method works really well for features like this. At this point, I believe myself to be a little bit undersized on width and a little bit undersized on diameter, so I'm setting myself up for one final cut that'll bring everything in. I check the width first with a stack of gauge blocks, and as expected, that's a little bit snug. That stack doesn't quite go in there, so that's good. That tells me how much I need to widen out to final dimension on width, and then for diameter, unfortunately, this groove is too narrow for my micrometers, so I am going to have to use the calipers, but if you're careful with the caliper, you can still get a measurement that's accurate enough for this. Then with those two adjustments in hand, I can now go a little bit wider and a little bit deeper and do one final cut in on one side, all the way across and back out the other side. And then verify that my diameter and my width came out where I expected. Now, normally when I'm building a steam engine, I actually prefer to do the eccentric strap first because it's much easier to fit these eccentric dimensions to the strap than vice versa. But the eccentric straps for this project are a long way away, so I'm going to make these now as Kozo says, and we'll just do our best to fit the straps to them if needed. Next, I'm going to take a number 1 center drill and I'm going to put a very tiny little center mark in the end of this. That's going to assist me with layout because the part is currently in the lathe and I'm all set up to be concentric with the OD and with the groove. It's going to give me a little place to put the dividers so I can get an accurate layout of where the actual eccentric portion of the eccentric needs to go. Before that though, I'm going to take it out and put it over in the mill while it's still easy to hang on to. I've got all the extra stock on the back because I'm going to drill the set screw in it now, and this is what holds the eccentric onto the axle. I'll get this centered up on Y, and then I'll find the edge on X that I can get the screw centered in the groove. There's different ways that people do this. Some eccentrics have a hub on them, which I actually prefer because it makes adjusting the valve gear a whole lot easier. But a lot of times people do it this way, where the set screw is in the center of the groove and completely covered by the eccentric strap, which looks very cool and it's very a compact design, but it does mean you have to remove the eccentric strap every time you adjust the valve timing, which is honestly kind of a pain. But that's pain for future Quinn, and she's a sucker, so we don't have to worry about her. There's the finished set screw hole. I also did that now because we're going to need it for a fixturing operation coming up. But next it's time to lay out the thing that makes an eccentric into an eccentric, which is an off-center hole. I'm going to do this with layout because this is enough accuracy for this job. If this is off a little bit, it's going to affect the stroke of whatever we're driving, be it the water pump or the lubricator, but there's usually lots of wiggle room in that. And doing this with hand layout is a lot easier than some other methods might be. So I'm going to center punch this, and then we're going to use that center punch after I deepen it a bit to set this piece up on the lathe for an eccentric turning operation. These are always super fun. The way I like to do this is to use my dead center as a tool for dialing in that off-center punch mark. So I set up the dead center between the punch mark and my live center in the tailstock, and then I dial in the dead center just as though it was a piece of stock. So if this dead center is running true with the axis of the lathe, then that punch mark is now going to be centered with the axis of the lathe, and we will have automatically achieved the amount of eccentric that we needed for this hole. You can also do this with a dial indicator. If you dial in the part central on the lathe and then use the indicator itself to offset the jaws of the chuck by the right amount, I think you can get more accuracy that way, but it is more technically difficult. I've kind of done it both ways, and honestly, because absolute accuracy of the stroke of an eccentric is usually not that important, doing it with hand layout is honestly quicker and easier, I find. Safety note on eccentric turning, you can only do this to a point. It depends how big your 4-jaw chuck is. You want to make sure you still have some of the flat part of the jaws touching the part, either on or close to the center line of the round part that you're clamping on. You want to really make sure that you're not clamping on the angled sides of the jaws. Those angled sides are really just clearance for adjacent jaws. They're really not gripping surfaces. So you can get away with this to a point. What you see here is right on the limit of what I'm comfortable with. Any more offset than this, and you really want to make a fixture. Make a larger disc that can hold this part with the hole off center the right distance. But this is going to be okay, and we'll just be careful. If I spin it up slowly, you can see how the punch mark, sorry that it's a little mangy, not a great punch mark, but you can see that it is centered, and the part itself is swinging wildly around that center in order to hold the feature that we want on the axis of the lathe. Pretty neat, I think. And of course you got to find the right RPM because we've just made a giant cell phone vibrator, and it will easily shake the whole lathe apart if you don't get the RPM just right. Sometimes faster is actually better than slower with eccentric turning. That just depends on finding where the lathe is happy vibrating and not vibrating. There's a certain resonance that it's going to have with a given mass of part. In any case, I center drill, pilot drill, and pre-drill that out for the subsequent operations. We do want good concentricity and roundness on this hole so that it's a nice close fit on the axle and that it's centered on the punch mark that we created. So after that pre-drilling, I'm now going to come in with the boring bar to get ourselves very concentric with that original punch mark. Make sure that the hole that we're creating hasn't drifted off of that eccentric distance that we want it to have. I'm test fitting with gauge pins now because I want to bore my way up to a good pre-drill size or pre-quote drill size for a reamer, because we're going to finish this with a reamer. This is a very traditional hole making method in machining. You drill and then bore and then finish with a reamer. Because drills are very fast, boring gives you concentricity, and then reaming is very good at dimensioning. This procedure is not one that I typically use. I typically go straight to the boring bar or straight to the reamer, depending on how much concentricity I need. But in this case, I kind of want the best of everything, so I'm doing kind of the best possible procedure, which is drill, then bore, then ream. Final test fit with the axle that this is going to be sitting on. It should be a nice sliding fit so we can adjust it, but of course no play and easy to lock in place with the set screw. That looks great. I'm ready to part it off now, but I'm going to semi-dial it back into a normal turning position because eccentric parting is very, very difficult and frankly kind of hazardous. You kind of want your part to be on center for parting, or at least more or less. It's a little bit of run out there, but that's okay. You really don't want the part to be swinging around and smacking into the parting blade on every pass. That's a surefire way to get chatter and also probably snap a parting blade. Parting blades being so thin and high tool pressure, they really want a very consistent tool pressure, a very consistent chip load. That's why parting goes much easier if you're skilled at feeding the cross slide very evenly and consistently. Also why a lot of people swear by power feed for parting. So one more gotcha for parting off eccentrics though is that eccentric hole that's flying around creates a challenging geometry for the parting blade. You can see as we break into that hole, you can see I've got a gap on part of the turn, so this becomes an interrupted cut for the parting blade. Not only that, but the shape of the hole being that it's a curve that's coming down on top of the parting blade and smacking into it on every pass, this once again can turn into an aggressive interrupted cut for the parting blade, which is not good. In this case, this is free machining steel and I'm going slow, so I got away with it, but I typically don't like parting parts like this. I parted that off over length, so now I need to flip it around and face it down to final length. But now it's difficult to hang on to. So for that, I'm going to put an extra chunk of that axle material that I have in the forejaw, and I'm going to use the set screw to clamp the eccentric on the shaft facing the other way so that I can face down that parting cut that we just did. I had to order the set screws, so I'm just using a regular screw for now, but I've got that clamping onto the shaft, and then I'm going to dial this in more or less so that the eccentric itself is on center, not the mandrel. Again, to make the parting cut a little less interrupted and a little more pleasant. I just did that by eye. It doesn't have to be that accurate, but the less interrupted a cut is, it's always better. You can see how the mandrel is swinging around eccentrically to hold the body of the eccentric more or less on center. Taking light cuts so that we don't overwhelm that little set screw, and that has gone just fine. That's the larger of the two eccentrics. This one drives the water pump, which has a longer stroke. I need a second one now that's smaller, and the steel that I grabbed for the second one was actually mislabeled in my bins. Stupid past Quinn, mislabeling things. So this was mild steel and not free machining steel. So this time I did use the hacksaw to part it off. Otherwise, the smaller one was done the same way, again, other than the stroke, which is smaller for the lubricator. I'll do a quick dry fit now to see how this is all going to go together. This also answers a question many of you have, which is why there's no suspension on the rear axle, because Kozo uses it to drive these two eccentrics, so you kind of need it to be stationary in the chassis for that. Now I'm sure you know that the crank pins need to be aligned on one side because they're going to be connected with side rods, but what you may or may not know is that the crank pins on opposite sides of the same axle have to be oriented 90 degrees apart. That's called quartering. And this is an extremely important step that we need to do now. You probably know that in general, calm down steam nerds, in general, steam engines have one cylinder on each side. You might have thought that that's to make additional power, but no, that would be internal combustion thinking, because remember on a steam engine, the cylinders don't make power, the boiler does. This is external combustion. The cylinders are just a conversion tool. They convert pressure and thermal expansion into mechanical motion. One cylinder is always enough for power making on a steam engine. Here on the Empress, for example, which is 4,700 horsepower, each of those cylinders is making 2,350 horsepower. And they're only like a 12-inch bore, so making power from a single cylinder is no problem in steam. However, the thing about a single cylinder in steam is that it is not self-starting. If that cylinder happens to be sitting near one of its dead centers, top or bottom dead center, then it won't turn over when you put pressure in, it'll get stuck. That's why when you start a single cylinder stationary engine, you always have to kind of give the flywheel a little spin to get it going by hand. That's obviously a deal breaker for a locomotive because it needs to start and stop in stations and back up in yards, and it's going to be stopping and starting in all different positions, all different orientations of that piston. And you can't have the crew get out and push if the pistons happen to stop in a place close to a dead center. So the way you get around that is you put a cylinder on both sides of the engine and you time the valve gear on those pistons 90 degrees apart so that one of the two pistons is always far away from dead center, and that piston will always get the whole system going when you start rolling. That's why we quarter the wheels, and that's what we're going to do right now. Now this needs to be reasonably accurate, but not crazy accurate, like close to 90 degrees. The main thing is that all of the axles need to be quartered exactly the same, of course, because they're all going to get connected with rods. But if it's close to 90 degrees, that's okay. So we're going to do this with a fixture that Kozo suggests in the book that looks like this. It's essentially a V-block that you put the wheel set in, and there's a little step on each side. And that step is the difference between the radius of the crank pin and the axle. And that ensures that the center line of the crank pin and axle will be 90 degrees on each side. I'm going to make that fixture with this piece of aluminum that I found in the scrap bin. I love it when I find a piece that's basically perfect for the thing I want to make in the scrap bin. That always super makes my day. I'm I'm going to cut this into 3 pieces over on the bandsaw, and then I'll clean up all of the edges on these to make everything nice and square. We don't have to go crazy here. This is a 2-time use jig, but I want it to be, reasonably nice. How nice you make your jigs and fixtures is always some sort of a balance between actually finishing the project and your pride. I mean, notwithstanding the actual purpose of the fixture or jig. Every fixture is going to have 1 or 2 dimensions and surfaces that are the really critical ones, because those are creating the references for the feature on the actual part that you want to make. So any error on those reference surfaces in the jig is going to get telegraphed into the part that you're making. So obviously that would not be great. In this case, really the only dimension that arguably matters is the 90-degree angle in the V that we're going to create, and the height of that little step that creates the offset for the radius of the cranked pins. But again, if there's some error in all of this, it actually doesn't matter that much, because again, what really matters is that all of the wheel sets on the locomotive are quartered the same way. If that quartering angle happens to be 88 degrees or 92 degrees, it's really okay. Kozo provides the drawings for this fixture though, which is really great because it's actually a very clever little fixture for doing this. Without this, I'm honestly not sure how I would have done it. I would have had to really sit down and think about how to do this, and I would have come up with something a lot more overcomplicated, no doubt. There are a lot of ways that people quarter wheels on the real thing. Locomotive machine shops would sometimes do this on their lathes, and sometimes they have these giant quartering machines that look a lot like lathes. Some railroad wheel turning lathes have a quartering feature on them that can be used for this, so there's different ways that they did it on the real thing, all involving gigantic machines. But here on the scale model, we can afford the luxury of just building a jig that's larger than the entire wheel set to do it. At this stage, I'm going to glue the 2 side pieces together and machine all of the V-block features together to ensure that they are identical. Arguably, I could have done this at the start and probably saved myself some effort, machined these pieces entirely glued together, but hindsight and all that. I could have made a shut up that's why joke here, but everyone's onto that now, so let's just say, because past me is dumb, that's why. After marking center on that where the axle is going to go, I took it over to the rotary table. I decided this might be the easiest way to do this. I don't know if I was right, but this did work, so stay tuned and watch how it went. I'll block this up on some scrap material, so of course I don't cut into my rotary table, and I'm centering up the punch mark there on the spindle. And I want to make sure I get the sides straight as well with the 0 or y-axis of the rotary table. The straightness of the V is not actually that critical as long as the angle is 90 degrees between the sides. That's really what matters, but I'll get this close anyway. Same with the center mark. It doesn't actually have to be perfectly on center as long as we, again, get a 90-degree angle in the V-block fixture. That's really what matters. Now I'm going to turn this thing to 45 degrees, and we're going to plunge straight down on that center punch mark with a 2-flute center cutting end mill. That's going to get this started. This end mill is smaller than the diameter of the axle that's going to be sitting in this V-block. More on that in a second. I'm going to plunge all the way through, and that's going to give me clearance for the final end mill that I want to use. I happen to have an end mill that is the exact diameter of the axle, but it happens to be a 4-flute non-center cutting end mill. You can see that the cutting flutes don't meet in the middle, so you can't plunge with an end mill like this. Thus, starting with that center cutting 2-flute end mill gave me the clearance so that I can plunge now down with this end mill and establish the radius at the bottom of my V-block. Of course, to cut a V-block to hold a shaft, you don't actually have to use an end mill that's the same diameter as the shaft. The reason that I'm doing this, though, is because it simplifies all of the math to make sure that the center lines of these cuts all end up in the right place. If you use a smaller end mill, then you gotta add in the difference in radius between the shaft that's going to be sitting in here and your end mill. Lots more potential for error there, and so on. So by using an end mill that's the exact same diameter as the shaft, I can just start on my center line of the V feature and make my 2 cuts, and I know they'll end up correct. After plunging my way down in a few passes, I've now created the left side of the V feature on both ends, actually the left on one and the right on the other, because the end caps are mirror images of each other, but I can still cut them in one setup like this. Now I need the other side of the V, and for some silly reason I decided to do this by rotating the rotary table at this point 90 degrees so that I can cut the other feature also on the y-axis of the mill. Of course, past me is dumb, and I could have literally just used the x-axis to get a nice 90-degree corner the other way, but sometimes you get locked into a mindset of how you're going to do something, and an easier way is sitting right in front of you and you just don't see it. That's why humans tend to work better in teams, because when we're left to our own devices, sometimes really obvious answers to questions are just not seen. Here's the secret sauce of this setup though. I now use the x-axis on the mill to offset this V-cut by the height of that little step that we need on the final V-block. Again, that little step distance is the difference in radius between the axle and the crank pin. So now I'm creating the other half of the V, but this side is inboard of where it would be for just a straight, pure V-block style cut. On the final pass, you can see how I've got a 90-degree corner there, but that second surface is inboard of the center line of where the original side was cut. I hope that makes sense. You can see it right there on the part, what it's doing. Now I go back down to near the bottom of that V, however, and I plunge in with the side mill and create a little more clearance. I don't want the axle to be sitting in the V-block pinned up against the bottom edge of that little step. That might cause an over-constraint and cause the axle to not sit in the right place. So I create a little bit of clearance by plunging all the way down to where the V side of this block would be if that little step was not there. This part is so much harder to explain than it is to just show you. I hope that you can just see what I'm making and it makes sense. Finally, I come in with a smaller diameter end mill and just touch off on the two insides of the bottom of the V to tighten up the corner radius in the bottom of that V block. Again, I want that radius to be smaller than the axle so that I don't over-constrain that axle. As with any V-block, when you put something round in it, you want 2 points of contact on the round surface, no more than that. Any more than that and you're over-constraining the surface and it might not be sitting exactly where you think. Finally, while I'm all set up and the pieces are clamped together, I drilled a couple of alignment holes, drilled and reamed, so that if I ever need to get these two sides realigned to fix an error or something in final assembly, I've got a perfect alignment pin feature on the two ends. This may or may not be needed, but it only took a second to do, and it's nice insurance. Then finally I drill and tap mounting screw holes in the ends of the bottom plate of the fixture. To separate those two halves now, I just dunk the whole sandwich in a bucket of acetone for a while. The acetone will wick its way in between those parts and eat away that superglue. You can also use heat for this and then clean up the residue, but these days I tend to just soak the whole thing in acetone. It seems to make the whole process a little tidier and doesn't discolor the parts or have other side effects that heat can sometimes have. So once that acetone is broken, then I dunk them back in there to clean up the remaining residue. There are the two pieces now unglued, and of course I flip one around because these need to be mirror images of each other. They're symmetrical at least, so I could make them together, but just need to flip them around on final assembly, which of course I almost forgot to do because past Quinn is dumb. Okay, here comes the cool part. You see how this fixture actually works. We put the crank pins in the wheels backwards, so they're sticking inwards. This is all very clever. Kudos to Kozo. Kozo kudos for this. And we set the wheel set on there, and you can see how the crank pins register against the step on one side and the same step on the other side. And just like magic, those pins are now perfectly quartered. At this point, I thought maybe it's a good idea to verify this somehow. Like I could put this thing on the surface plate and take some measurements and make sure that these pins are at 90 degrees. I could probably also do this on the mill with the DRO and an indicator. At this point, I actually consulted with my patrons, most of whom are smarter than me. And of course, we know this distance here between the crank pin and the axle. So if we can measure either the horizontal distance between the crank pin and the axle or the vertical distance, then we have enough information to do some trig and see what angle that pin is sitting at. Half my viewers suggested that, and half of them suggested I was way overthinking it, and if it's close to 90 degrees, it's good enough. So that's what I ended up going with, the group that was voting for less work. I double-checked my V with a square reference, and it's perfectly square, so it's going to be fine. Again, as long as the wheel sets are quartered the same, that's what's really going to matter. Honestly, if they were at 80 degrees, it would probably be fine. Time for this fixture to earn its lunch. I'm going to clean and degrease everything so that we can Loctite the wheels onto the axles. You might be expecting these to be press fit. That's certainly how the real thing is done. However, Loctite is actually a really good choice here. First of all, according to Kozo and Henkel's website, Loctite properly applied is actually stronger than an interference fit. Secondly, I really don't like doing press fits on cast iron parts. Cast iron is quite brittle, and I have absolutely broken parts trying to do press fits on them. So I don't want to risk that at this point. And third, there actually isn't that much force on these axles because remember the side rods and the connecting rods are driving the wheels directly from the pistons. There's not a lot of power being transmitted through the axle. It's not like on an internal combustion engine where the axle is transmitting all of the power through it into the wheels. So it needs to be strong, but not crazy strong. One funny little gotcha here is that the wheels have counterweights cast in them to offset the weight of the connecting rods, which is good, makes everything run smoother, but it means the wheels didn't want to sit along the sides of the fixture. They kept wanting to roll themselves back so that the counterweights are facing downward. I had to tape everything in place while the Loctite sets. I'm also extremely proud of myself for having remembered to put the Eccentrics on before attaching the second wheel permanently. The front wheel set was done the same way, of course, but there's no Eccentrics on that one because this sits inside the moving axle box. Once the Loctite is set on those axle sets, then I can turn them on end, and I use this little rigged fixture to install the crank pins. These are also done with Loctite. These were pretty snug, so I wanted a fixture set up like this so that I have the option of tapping them in if needed. A couple of them did need tapping in. Once all that was set, now I can try installing them in the chassis. Finally, the bearing caps with the upper halves of the bearings go in place on top. I don't know if I've mentioned this, but all of this stuff is center punched, including all of the bearing halves. There's tiny little punch marks on the ends of them, so all of this stuff always goes back together the same way and in the same direction. And that's pretty good. It's a little bit on the snug side. It's running smoothly, but it's a touch snug, so I did do a little bit of clearancing. The main issue was the thrust faces on the outsides of the bearings needed a little bit of room added. It was difficult to get the wheels in exactly the right places on the ends of the axles. A couple of them ended up a little bit inside of flush with the end of the axle, which caused some rubbing on the fronts of the bearings. Now remember when I said you always put centers in the ends of your axles in case you need them someday? Well, that day is today. After assembling all the bearings, things were still a little bit tight, and I decided I would add a little bit of clearance on the axles. I want these axles to run really freely in the bearings, with no slop of course, but freely enough that I won't have any tightness issues with the valve gear moving forward. So I decided to set the rear axle up in the lathe and do a little bit of polishing on the areas that are running in the bearings. It's all very close and it would probably run in, but I want it to be free running now before moving forward. I don't want to try and be diagnosing 50 different tightness issues at the end. I'd rather keep things moving smoothly as I go along. This next part was kind of an aha moment, which many of you pointed out on the video where I made the axle box. I was wondering why the bottom of it was open like this. Well, this is why, because once the wheel set is assembled, lowering it down from below like this through that open slot is the only way to install the axle in the axle box. Of course, on the real thing, they do this from above. The locomotive is actually lowered down onto the wheel sets with a giant overhead bridge crane. That's actually still how they make locomotives. Go check out pictures of like the EMD and GM factories where they make modern diesels. They still do it that way with enormous bridge cranes carrying the entire top of the locomotive, which is then lowered down onto the chassis. It's all very cool. But the point here is, if the bottom of the axle box wasn't open, well, I'd be sad right now. That little bit of polishing did the trick though, and that axle is running really smoothly now. I like that a lot. There's still a little bit of room for run-in, but it's running freely enough that I know it's not going to be a source of drag when I'm trying to debug drag and contact issues in valve gear. Now she's finally back on her wheels for real this time. Everything is permanent, no lies, no YouTube trickery. Everything is where it's supposed to be, hopefully for the last time, and I can roll it back and forth as much as I want because everything is attached. That little fixture worked like a champ. Again, kudos to Kozo for that design, very clever, and everything is looking really good. We are ready for valve gear. We're going to be doing side rods. We're going to do piston rods. We're going to do wall shirts things. It's going to be amazing. Stay tuned for all that. Thank you so much for your support, for watching. Thanks to my patrons for making all of this happen every week, and I will see you next time.